Welcome to one and all. This is Ganesh. On behalf of Autodesk Student Community Support, I'm making this video tutorial of simple stepped path from a strength of material book by author S. Sandil to proving the inventor analysis accuracy. Coming to my problem. Here's my problem. A bar of steel 0.7 meter long for the first 0.2 meter, it's about 25 diameter, and for the next 0.3 meter, it's 20 in diameter, and for the remaining 0.2 meter, it's 15 in diameter. Here we are asking to find change in length del L if subjected to a tensile load of 1 lakh Newton. The value of Young's modulus E is 0.210 meganewton per mm². Here the problem is clearly stated in the sketches. It's about a 0.2 meter for dia of 25 and next 0.3 meter dia of 20 next 0.2 meter is dia of 15 and axial pull of 1 lakh Newton. If we start doing this problem in Inventor and we get a structural analysis, static structural analysis, I'm skipping to the Inventor. Here my inventor is open. Let us start doing this problem. Just click new. I'm going to metric, clicking on metric. I'm going to do a part model in standard IPT. It's a default template. It's about a part model, units of millimeter. Just click here. Here my home window starts. Go to create sketch, create 2D sketch. Click on create 2D sketch. Here my plane comes. I'm choosing one plane to sketch. Here my sketch tool comes. I'm starting with a circle. Picking my circle, giving a center point. It's about like a 25 diameter. I'm just giving 25 directly and clicking enter. Then finishing the sketch. My part modeling window comes. I'm giving x2. For first off, it's about a 0.2 meter. It's like 200 I'm giving 200 I'm zooming out. Just click OK. Then use this face to sketch. Pick this face and give create sketch. Again my sketch tool comes. I'm using this center point. It's 20 I'm giving 20 directly and clicking it. Finish sketch. Again x2. Right now, careful on choosing the profile. Here we have two profiles of selection. You need to select the inner profile. I'm selecting the inner profile. It's about a distance of 0.3 meter. Then it's 300 Giving a 300 click OK. Again, use this face to sketch. Select that face and give a create 2D sketch. It will come to normal. Again, start with circle. It's about 15 diameter. I'm just giving 15 directly and entry. Finish sketch. Again give x2. Choose the inner profile. For 0.2 meter, it's going to be x2. Then it's 200 Click OK. If you see, my part model is right now is completely done. I'm going to do analysis, carry out analysis for this part model with an axial load of a 1 lakh Newton. It's like a simple cantilever beam. One side is fixed and the axial load of a 1 lakh Newton is going to be applied. Go to the environment tab. Start with stress analysis. Getting into stress analysis, just give create simulation. It will ask a settings, static analysis settings to detect rigid body modes, or it's like in a shell concentration tolerance and all. We just give OK directly. Our analysis tree TB appears on the left corner. Here my part model is wrong. Whatever the analysis is going to be carried out, we need to give a material. I'm giving material. Right click, just give assign material. Initially, I did not define any material to this part model, so it's showing a generic without empty. We'll override the material. We don't need to give a material. I'll just overriding the material just by picking this upside arrow down. Give as, we know that it's a steel. I'm just giving steel to this. Here it's asking about a safety factor. We know that safety factor is yield strength by working stress or by ultimate stress by working stress. It's really good to calculate through yield strength, so I'm using yield strength. Just give OK. Here its next string is constraints. Right click. Here we are going to give fixed constraint. Since I said it's like a candido beam. Fixed constraint. It is asking to choose the face. I'm just rotating the part model to choose my backside face. I'm picking this face and giving apply. My constraint is done. It can be noted by plus is added to this. If you unplus it, my fixed constraint will be there. If you just drag a mouse over there, it will show where it's fixed. Next, go to loads. Right click. Here we are going to give a force load on the other face. I'm picking the face. Arrow mark indicates on what side the direction, but we don't need this in this direction. So I'm picking a direction. It will flipper my load side. It's about like a 1 lakh meter. 1, 5 zeros, 1, 2, 3, 4, 5. Apply. When my load is applied, it's about a contact. If it's going to be a large huge problem of a biggest assembly, we need to give a contact. Right now we having only simple single part, so we don't concentrate on this part. Mesh. Whatever the problem on whatever analysis you are going to do, it will be in a mesh. Since we are splitting this part model into finite elements, so it's about a mesh. By right clicking this, we having a mesh settings. We can change the mesh element size. Here the element size is 0.100 and a minimum element size of 0.20 and the grinding factor is 1.50. Maximum turn angle is 60 degree. It's not all default. You just if you want to change it, you can change, or also we do go ahead with this. Everything is done. Right now just give simulate to run this analysis or compute. I'm running this analysis. It will take some time to compute. Here it's a simple problem. It will be computed too soon. Here my analysis is done. Starts with 1 resistors. Here we are getting around 1 resistors of around 872.4 megapascals maximum and minimum of 46.3. If you want to animate, you can give animate. It's near to the simulate. On a result tab, we'll have a animate. Just click animate and we can play this to know how it's going to be before. By changing the step size, we can make the speed 100. It will make too slow. It's right now the normal. If you want it fast, here my animation is doing it fast. Even we can record using this app. Then we did this problem to calculate the displacement. We directly go to the displacement. Double click on displacement. Here we got that the maximum displacement result as 1.193 maximum. It's about in a unit of mm. I have a PPT to prove that. For that problem, on doing a manual calculations, it's about like a 1.187 mm. We got around like 1.19. Yeah, it's about a second decimal is changing over. Inventor is almost accurate. If you need this accurate result of 1.187, by getting down this mesh size, element size, we can obtain this. Even we having a many results is computer over this. It's like a safety factor. We having a minimum of a 0.24. Then this is a failure. We know that if a safety factor is going to get down the 1, less than the 1, product is failure. Here we got only 0.24 minimum, so this is failure model. Then we can compute the stresses on particularly on XX and XY, XZ, YY, YZ and ZZ. Even we can compute the displacement particularly on single direction. Let me check on X direction. It's about 1.193. In Y, it's going more. It's a too negligible since our axis of a stepped bar axis shaft is on towards X. Even we can compute this. Even we can get as a report just by clicking report. Autodesk Inventor make a own report. Here's my author. This is Ganesh, and a logo. What type of logo is going to be, and summary of the problem, properties, and simulation format. On what format you need. Just give OK. Here my report is getting generated. It's too easy on Inventor to create a problem with a report. It will take few seconds to generate a report. Since we have nearly results like a warm misses and stresses on different direction and displacement on 3 different directions and strain on 3 different directions with the combinations. On a background you can see this. It's creating a report with different image shots, screenshots. My report is getting done. It will be initially like a HTML font. Yeah, with the Autodesk logo. We got the report. Here we are having a physical properties, water density and mass, area, volume, and simulation, material. As I selected a steel, it's saying a mass density, yield strength of a steel, ultimate strength, and a Young's modulus. Even we see that it's a 0.21. It's about 210 gigapascal. Steel is having the same material. Here my model is with a constraint, where the load and constraints and everything with the 2 different snapshots. Here I get the result summary of the total result. Starting from the volume, mass, on is starts to the strain. Everything is computed, even with a screenshot. It almost like nearly 18 to 30 screenshots, images of different results. It's too easy to get a project report on Autodesk Inventor. With this, I'm signing out. Thanks a lot for watching this video. Myself Ganesh Tenyanam. My email ID is ganeshhr555@gmail.com, and my phone number is +91 99 52 11 9645.